Hey guys, Steve from Vorsprung Suspension in Whistler here. Welcome to the Tuesday Tune. This week we're going to be doing something of a Mythbusters episode where we look at a few common misconceptions and basically clarify or correct those. So there are a few different things that we'll cover. The first one is the concept of mid-stroke support. So we often have people discussing mid-stroke support of their fork or their shock in some context, and what this usually translates to is that they want to feel like they have more to push against in the middle of the stroke. From a technical point of view, a very linear spring rate will give that to you, more so than a very progressive one. However, what is also very common is that people's perception of what is the middle of the travel is actually quite late in the travel, quite deep in the travel, and they are pushing a long way through. And so when we talk about, bottomless tokens or volume spaces, not really increasing mid-stroke support in the strictest technical sense, that is correct. But if what you're feeling is actually that you are riding too low in the travel, you're at 80% travel when you want to be at 60% because you're pushing through too easily to that point, then you might find that yes, increasing the progression of your spring rate, if it's an air spring, using spaces, volume spaces of some description, can help. And to illustrate that point more clearly, I've drawn up a quick graph here, completely linear spring rate here, 1 million token, hyper progressive air spring curve here, the initial stiffness notwithstanding. If you compare to the sag force here, obviously the force pretty well everywhere in the travel is lower with this more progressive spring curve. However, if you look at the gradient of this line here compared to this one, even though we're running like 50% sag or something ridiculous with this setup, this gradient here is stiffer beyond the sag point than the completely linear setup. So in that sense, you would feel that it is something firmer to push against. However, if that's overridden by the perception of it being too deep in the travel, that's what we need to really ascertain and work out. Do you want something that has a higher force in the middle of the travel? Do you want something that has a higher stiffness in the middle of the travel? They're not necessarily the same thing. Stiffness being force divided by distance. So that's number one out of the way. Number two, we quite commonly get asked about this. Do titanium springs perform better than steel springs? The simple answer is, if weight alone is your metric of performance, yes. If it is anything else, no, they are essentially identical. They do not respond faster, they are not plusher. A spring rate is a spring rate. This is 450 pound-an-inch steel spring, coil spring rate. This is also 450 pound-an-inch titanium spring rate. If you are genuinely feeling that your spring rate is softer with the titanium spring, there are several possible explanations for this. First of all, it could be that your spring is actually softer. Not all springs are exactly as they are rated. Most quality ones from the brand name manufacturers are actually quite close, within a couple of percent. Some of the cheaper titanium ones are not so accurate, some of them are bang on. However, if you are feeling like your titanium spring is softer than your steel spring, either it's placebo or you have a different spring rate. Alternatively, you have a different amount of preload wet rod and you're measuring a different sag value. However, spring rate is not material specific, it is defined as force, change in force over change in distance basically. Whether that's steel, whether that's titanium, you will not change the performance by changing the material. The third common misconception that we hear is basically misuse of the term cavitation. So we'll commonly hear people say, something is cavitated, or they have cavitated oil or something like that. Cavitation is not foamy oil. It's not air in your oil. That's aerated oil or foamy oil or air in your oil, or whatever you want to call it. Cavitation is a purely dynamic effect. It occurs when the amount of pressure drop that a particular valve would generate at a certain speed is higher than the available pressure ahead of that valve that's able to push oil through it. This is how valves are characterized externally to a damper, but this is effectively the same sort of thing as a force velocity curve that you'll commonly see from a damper dynamo plot. Pressure drop over this piston here, this one in the middle, is effectively what gives us a damping force in a monotube system like this. So here we have a gas charge pushing an IFP. IFP pressurizes the oil, And basically that means that when this compresses, it's that pressure here, that pressure of the oil, that forces the oil through the valve, through the shim stack, through the low-speed bleed, whatever it may be. Now, basically, if you push this fast enough that this pressure is no longer sufficient to force oil through the valve at the same speed that this is moving, then it will just begin to push this oil ahead of that piston. It will draw a vacuum behind it. Once you drop below a certain pressure, effectively what will happen is, because you're drawing a vacuum in that oil, it will locally evaporate, and that is the phenomenon known as cavitation. It is the same sort of thing that happens with boat propellers, actually in a very localized position right behind the tip of the propeller, where the vortex shedding can create a locally very low pressure that actually means that you are essentially evaporating water. But in this case, what's happening is you are effectively boiling very temporarily the oil behind here. You're drawing a gap, basically a cavity. And so what will happen there is that as this slows down, if this is able to basically catch up on forcing oil through, then it will largely function okay. If it's not, however, and usually it isn't, what will happen is that as this changes direction, we suddenly have a gap here where we don't have essentially a solid volume of oil behind the piston. It will knock in rebound. Obviously this is very bad for performance. There are very few forks or shocks on the market that have an issue with this right now. They're mostly designed in such a way that this is not a problem. There are a couple out there that are right on the edge of that, but right now, I'm not here to name and shame. This pressure drop versus velocity characteristic, once you reach the velocity here, that you generate a pressure drop that is higher than the gas pressure or the damping pressure from a base valve is able to provide over this, that's when you run into issues with cavitation. That is why some monotube shocks are charged to extremely high pressures. Some of the Fox Float series ones, for example, go to 500 psi. Simple, right? So next up, we're going to address something that has been used multiple times over the years by various companies, usually probably as a semantic error rather than anything else, but as essentially a misleading or at least technically incorrect marketing claim. Now, this, before I start on what it is, this here is a graph that shows, this red line, essentially the maximum velocities that you will see anywhere in the travel, in compression and in rebound. Now, we have touched on this before in some of the Tuesday Tune videos. Essentially what happens is that the highest velocities occur very early in the travel. They don't occur right at zero because it takes a certain amount of displacement and acceleration before you reach your peak velocities. Basically they happen very early on, probably proportionally even earlier than I've drawn here. And then they stay fairly high through most of the travel, and then towards the end of the travel they drop off as the spring forces pick up and whatnot. So the reason for this is typically that the highest velocities are encountered when there is the lowest resistance, meaning the lowest spring force. And likewise in rebound, the highest velocities in rebound occur when the spring force is at its highest. So rebound peak velocities drop off as spring force drops off, because the only thing that is acting to extend the suspension is obviously the force of the spring minus the force of the rebound damping. So what we've seen advertised here and there over the years is speed sensitive damping, which is basically any shimmed valve, popper valve, whatever, anything that isn't a SPV or boost valve setup that is an inherently position sensitive damper. But speed sensitive damping that will give you, a plush initial stroke, but ramp up to resist bottoming out. So ramp up, how? Is it a more progressive damper curve in terms of generating disproportionately higher forces at higher speeds? Typically not, because that will give you something that becomes quite harsh and very unsupportive initially. Or is it something that ramps up towards the end of the stroke, as we've seen explicitly advertised by a current product? Obviously that isn't possible. A speed sensitive damper reacts the same way to a certain speed at this point in the travel as it does at this point in the travel. The only difference really is where those maximum velocities occur on any given hit. you cannot use any combination of shimmed valve that's currently on the market to create something that actually gives you less damping at the start of the stroke than it does at the end of the stroke. None of these dampers are amplitude sensitive or position sensitive like the boost valve systems were, which relied on IFP pressure holding the valve closed. And so those claims are essentially, if nothing else, semantically incorrect. Anyway guys, that about does it for this week. Any questions, comments or suggestions, please leave them in the comments. We always like to read them, and until next week, we'll see you then.